mean field theory, because one of the fundamental results of Ginzburg and Landau was to prove that fluctuations above a certain critical dimension that's specific to that universality class, they are Gaussian, so they are weak in a sense. Below this particular dimension, they become so strong that they change the critical properties. They change the critical exponent. So the correction to the Landau theory of critical phenomena originally is they are very strong. But it's nice because at exactly the upper critical dimension, the theory is Gaussian. So it's mean field. So it means that we can do systematically some correction using our ability to do Gaussian integration, if you want. Because all perturbation theory is based on our ability to solve the Gaussian theory. So now, if you want, assuming that as a fact, that if you want, we cannot prove, there was a question that was posed yesterday by a professor there, we cannot prove that universalities classes exist in all the range of integer dimension below the upper critical dimension, but it's a fact in a sense, because we have that, especially the one component cases like this. And when we have multi-component, universality class can disappear because it can become first order. But in any case, it's a first order transition. So having a map, even if it is a ghost universality class, it helps you to have this idea. So thanks to this, we come to the point after this general relation that a universality class is basically in one component case is basically labeled by the upper critical dimension. Okay, and we have seen that it's a very simple topological algorithm to find out the upper critical dimension. It's just an extension of the traditional power counting, something that we do in a moment. But there are already two little things that were somehow missed in the literature. So the first one was not missed, but it's not common knowledge. It's the fact that most universality classes have a leading order which is not one loop. We are so biased by the fact that we look at the renormalization in 4 minus epsilon dimension that we think that everything has to be described in 4 minus epsilon. That's not the case. So you have to enlarge your mind and understand that no, once I decide the DC, I am actually pointing at the universality class. It's a strong constraint deciding in DC. And most DC have leading order which is bigger than. So most of the information relative to the renormalization group is hidden somewhere in the loop expansion. So you need a map. And the second fact is that most DCs are rational numbers. So we are, and this makes sense, okay, completely sense, and actually I will show you some example. And in particular, while the even models were known, the one upper critical dimension was missed in the literature, and we discovered that. And we were the first one to compute the beta function of this system. And this is very interesting because this is the only other one, together with 6 and 4, that has upper critical dimension above 3. So it's one of these lines that can generate something which is non-trivial in 3 dimensions. And this is also important when you go to the multi-component case, because it means that there is a whole family of universality classes at any order of n components that can be non-trivial in 3 dimensions. So it can be a non-trivial conformal field theory. Okay, and since the possibilities for the multi-component, the types of symmetries, because the main question that I want to address is that by following this approach, we come to the point where we are exchanging, we let the RG give us the symmetry. Normally, when we speak about the normalization group, we say that a universality class, a phase transition is determined once we say the dimension, once we say the type of degrees of freedom. Here we're working with those which are representable as scalar, with a caveat that many theories which are actually fermionic at the fixed point can be described as scalar, so it's not so restrictive. The point, and and when we go to n component, we will, and this is one of the best things of this approach is that we will be able to write down the general beta function for an n component. So we will be able to write down the general G, and so the fixed point of this big system of equation are all the possible symmetries that can be represented physically by an order parameter of a certain type. So we are really computing symmetry. We are rotating the things. Normally we said that, okay, we fix the symmetry and the RG, and we do the RG. No, now we can do the RG, and the RG will fix the symmetry. Okay? And so Then there is another thing. We are working in dimensional regularization, which has its pros and cons, clearly, because dimensional regularization is somehow a borderline approach because, for example, it's difficult to work with dimensional regularization in 3 dimensions. So we're so interested in 3-dimensional theories. But here, we cannot apply that. Yes, we can apply it only for the critical model. But we cannot, what we would like to do is to apply directly the RG of this form to the easy model in 3 dimensions. This is possible, and this is, but we need a non-perturbative approach, which I will introduce later or tomorrow as a complementary of the thing that we're doing. And so what is nice about dimensional regularization is that the contribution to the beta functionals, so then the other novelty for us is that we work in terms of beta functionals. So which means that these things, they are function of the field evaluated at the constant background field. So in all our approach is built out of the background field. And we have these 2 objects, which we will see today, they are the generating function of the beta function. So by computing this, we compute all the beta functions, okay? And furthermore, these things have to have the dimensionality. This is dimensionless, and this has dimensionality of the critical, okay? Because this is a potential, and this is... So thanks to this, the type of monomials, the contribution at every loop order are fixed by the other argument that we did yesterday. Very simple, the Euler relation, just a realization that we need to know much less than the enumeration of the diagrams, which is something that we can do in any case, but that is another constraint, another working. And in a very simple way, you can write the code, and actually you can write a code where you make this table dynamical. You just specify the number of loops you want here. For example, if I specify 5, then the lines will be all the dimensions that are switched on before 5 or equal to 5. And then if you will know which are the zeros, you will know which entry will have something, and you know which is the monomial or the sum of monomials, okay? And that's all the information. Now you need to fix the coefficients, and now we are discussing a little bit about that. And after this, you have your table, and this is basically the summary of universality classes. So this is all that there is basically in DSG. And this is the n equal 1 component case. And then the beautiful thing is that most of this table doesn't change when we go to n components. But even in 1 component, we have a great simplification with respect to the approach of computing the beta function. Because there are only, for example, 2 coefficients here that we have to compute, the leading and next to leading order, okay? And actually they are very simple coefficients, if you see, okay? And the question is, how do we compute these coefficients? So there are various ways. And the first way is simply the one that, okay, let me evaluate. So this is the Ising model. Now let's focus on this one. The beta functional of the Ising model is a constant times v second square plus another constant v second v third square. This is how it is. Now we need to determine A and B. So we could just plug inside the marginal potential. And then this one will give me back the beta function of the marginal coupling, which it's already known. So fixing A and B that way is not cheating, because we will see by buying from the market, from the calculation done by other people, 1 beta function, we will actually generate all of them. We will show that most of the beta function, for example, in all textbooks, you compute the beta function of the mass, and the one has 2 different calculations. No, it's always the combination of this A and B. So already this reorganization of the information is very useful. And also, if you do it like this, then you can directly buy the theorem, the standard, let's say, proof that the leading and next to leading order of a beta function, 1 loop or 2 loop normally when we speak about, but in general actually this is leading and next to leading, they are actually scheme independent, okay? And since the coefficient of the marginal coupling beta function, or exactly function of A and B, this already shows that A and B are scheme independent, okay? There is also a more general way that we see later to see that. So basically these coefficients A, B, and then in the case of Ising, the one of the anomalous dimension, we can call them the universal Epsilon-Expansion data, because these are the only numbers that we combine everything which is scheme independent. So everything that the Epsilon-Expansion can tell us is encoded into little numbers. What is interesting is that now at the functional level, we can take a different route to compute A, B, and C, which is one anomalous dimension. That is interesting because, for example, we are so used to think, this is the one loop contribution. So from this one, we will generate the standard beta function that we wrote yesterday, the beta function of lambda, which is equal to 3 lambda square divided 4 pi square. Normally, we do a one-loop computation to do that. Within interacting theory, phi to the 4. But now you see that this thing here is quadratic. It's two derivatives. So you see that if now I plug inside here, just if I take this potential, okay, let's see. So I have the beta v is equal to a v second square. How to determine a? Let me choose a potential which is just what I write here. It's just lambda 2, okay, the mass, but I will just use this general way of calling them in this way. So clearly, b second is equal to lambda 2, okay? So it means that, now, what is this? What is beta v? Beta v is beta v has an expansion because I can write, so this will be equal to the beta of 0, okay, plus, if you want, the beta of 2, 1/2 square, and so on, okay? So in particular, if I just evaluate, if I just plug this one inside here and evaluate everything at zero field, I will just obtain the relation that beta 0 is equal to a lambda squared 2. So I just need to take a non-interacting theory. So the non-interacting theory, which is trivial to compute, gives me the coefficient of the vacuum, which is a. And as is the standard thing in quantum field theory, the contribution to the vacuum, they are 1/2 the number of degrees of freedom. And then you have the standard 4 pi square. So you immediately see that a is equal to 1/2 and the pi. Again, this amounts to the same. Now we see we have computed this indirectly, which is normally a one-loop computation. That it's not easy. After you know it, it's trivial. But the first time you encounter it is a little bit more than trivial. You need to renormalize. You need to take you have to look at this kind of diagrams and so on. No? In reality, you don't need to go all that way because seen from here, there is just a 1/2 that comes from 1/2 the number of degrees of freedom. So it's very, very crispy. Similarly, what is interesting is that, okay, now let's go to the next leading order, so to the two-loop contribution. Well, now I can choose a potential, so which is now the simplest choice that I can have to have it in zero term. You see, I do not need the lambda 4 coupling. It's enough to have the lambda 3 coupling because I have only this diagram, this thing here. So it means that basically this coefficient is in 1-to-1 correspondence to the pole of this diagram without the need of counterterms, which normally you need, that normally come from the other diagram when you do 5 to the 4. It's a little bit more complicated because here you really single out the contribution. What is this? This is just the factor -1/12 that we have seen from the loop expansion. There is now V3, this is lambda 3 squared. There is a lambda 2, okay, which is here then I just use the Schwinger parameters. This integral is very simple to evaluate. You just do the standard redefinition of S is equal to S1 plus S2 plus S3. I give it as an exercise, okay, because it's just, but it's the simplest way to compute this thing. It's simpler than the normal route that we normally do to compute the two-loop contributions in the 5 to the 4 theory. And we do not need, so we have computed all the information that there is in the 5 to the 4 theory, but not only, because we will see that this applies to the ON model, to whatever model with whatever symmetry. These are the two numbers that you need. And you see they are very simple, a 1/2 and -1/2. Okay, yes?
So you said that you don't need counter terms.
Yes. No, you don't need it because in this case, you see, there is no, this theory doesn't have any other divergences, lower order. So this is a theory, this particular theory in 4 minus epsilon has the first contribution at Chulu. So, and so yeah, it just pinpoints down. Clearly you can do the computation, and this is another, that's nice, doing the standard loop expansion, keeping a normal potential, and you will recover after all the steps exactly this form with the right coefficient. But we have taken the easy road, okay? Yes. Yeah, it's the guy from upstairs. He's
Can you go back one second?
yes. Then I will give you the slides in any case. So.
Yes. Thank you.
And now let me do a nice. Now we need to compute the other number, which is this one. It's the -1/6 of the anomalous dimension. Okay. So this is the table of the anomalous dimension. Again, also for this one, you can do it systematically. And if you are interested also in all the irrelevant and the mixing terms, you will have higher order functionals. For example, there are 3 functional with 4 derivatives. And the z factor will also enter. Now this is a kind of, now we're looking only at the relevant and marginal sector, which makes every functional only dependent on the potential. If you go into the mixing, then you also, the other functional will enter. But again, the systematics can be done, and you can foresee the general RG structure of all these functions that run with contributions, and they all have these coefficients. Some of them are universal, and you will pinpoint the easiest way to compute them, and the other one are scheme dependent. So you can even just probably imagine a way of proceeding where you just give them a name, and maybe you just prove they are positive, negative, and make your general conclusion, because in any case your conclusion should be independent on the scheme. So it's an abstraction that pays back a lot. So now let's try to compute the term of beta z. Here I show you a couple of slides where I show you another approach, because beta z is equal to c before square. Okay? We want to compute this. So this number here is directly related to the anomalous dimension, because the anomalous dimension is just minus beta z, okay, evaluated phi equals 0. Okay? Because remember what is beta z? Beta z is the term which is in front of the cinetic term, and so it's the 0 part of this functional is the standard wave functional normalization. And so this is equal to minus c lambda 4. Now, yes, I'm considering, for computing this, I need to consider lambda 4. Okay? But now I want to show you another approach that actually I will comment on it. It's called, so now we just need to compute the anomalous dimension in the Epsilon-Expansion. There is a root, this root here, which is very simple, is actually the simplest I know. And it comes from an approach which we call Schwinger-Dyson-Plies conformal field theory. So it's we made several papers on it. Actually, we constructed, me and my collaborators, we started working on this because we wanted to construct this theory in 10/3 in a way which was independent of perturbation theory. And in particular, because I will show you that one of the things that we do with this functional approach is also compute OPE coefficients in the Epsilon-Expansion. That was never done. And we also compute them in CFT, and we match them. So, but here we don't need the whole machinery of this thing. Here we just use standard scaling. So this is a different way of doing so we know that the 2-point function in a scalar theory at the criticality has a scaling form, no? You know this formula. And this formula here you have d minus 2 plus anomalous dimension. In 4 dimensions it's 2 plus eta. And this is alpha. Alpha is the normalization of this thing, which is non-trivial. So now we also know that we are in phi to the 4. So if we are in phi to the 4, we have that actually this field is a descendant in the length. This thing here is a descendant of the field. So these are the equation of motion. And Schwinger-Dyson's equation are basically telling you that you can insert this one as a 0 in every correlation function and it will be 0. So this is basically the way in which when you go away from the Gaussian fixed point, you start saying, okay, not all operators are independent, some of them are descendant or something else, and this equilibrates in a conformal field theory, which is non-trivial. So the idea is this one. Let's look at this very simple expression and let's take two Laplacians. So we act on the left-hand side and on the right-hand side. So on the right-hand side, this is just a function. We know very well how to make the derivatives. And okay, I will give an exercise to check the calculation. It's nice if you've never done it. It's interesting because this gives you, gives you something with 6 plus this, which is basically related to the fact that, but then gives you a non-trivial polynomial in eta. Now, this is in the interacting theory. But now, when the interacting theory is near to it, so this thing here, this first part here, this is true. Okay, now if I put D here, this is true in every dimension. So now I'm gonna work so this thing is non-perturbative in a sense. But now I go near to 4 dimension, and I just want to get the leading order contribution. So you see that this thing here is proportional to eta. Okay, so I will put alpha, which here has the non-trivial, and it's a non-trivial problem computing this constant in interacting theory. But I will put it to the Gaussian value, and I will omit the anomalous dimension here. And I get this expression. So this is the leading order in epsilon away from the fixed point, from the Gaussian fixed point. I know the Gaussian value of this. Now I use the equation of motion, and so in the other side, the derivatives go inside. They are an x and y, so they hit this one and this one. So I can use the equation of motion and I get this correlation function times this thing here. So now again, I can evaluate this one near to the Gaussian fixed point and just want to get the leading contribution. The leading contribution comes when I evaluate this one with the Wick's theorem, the standard gives me 3 factorial that eliminates 1 3 factorial. I have lambda 4 square, and then this thing here it goes to alpha cube g. Now I just need to equate these two things. So you see I have a formula for eta. The formula for eta is this one, which gives me this one. But now I just take this one, I compare it with this one, and I read off that c is minus 1/6. Okay, so this is all. We did all the calculation. We didn't skip anything. Okay, and this is to compute leading order anomalous dimension is actually the fastest route. Not only it gives us some interesting non-perturbative equations that one can study in another direction. I don't have time to speak about that, but this could be a point for attempting finding new strategies to compute eta. Eta is like pi. So if you look at the history of pi at the beginning people started to compute it in a very obvious way, like inscribing the polygon. So that's somehow the RG. You just do the stability matrix. Then we discovered that with conformal field theory is a trick to do a little bit better. But then there are, in the history of pi, the best result comes from very simple ideas. And maybe there are simple ideas. I mean, we should, I think that in our lifetime we should be able to see eta with 100 digits. It would be nice, because it's really a pity that even the bootstrap uses a quantity of computational power, which is incredible. I mean, it's an intensive computational thing to compute 3-4 digits of this number. In any case, for us, this is just a way to do this. And actually, this applies to most of the entry of the table of the anomalous dimension. So this is actually my trick to compute this. And so you see, in this way, we fill, for example, we fill all this diagonal, I fill it like that. It's exactly the same computation. Just in place of phi to the 4, you use phi to the n. And you compute all these things here. Okay? And then you can just invent yourself a method. What is important is that we have highlighted which are the numbers which are valuable to be computed and which are the numbers at the root of all the other numbers. So,
but you compute the Laplacian?
Huh?
You will compute the Laplacian for the...
Yeah, for example, if you want to compute, as an exercise, these entries here, you do exactly the same thing. but you do it with different power here.
Okay.
A little bit different combinatorics, but you get the closure formula for all of them. And then, so there are, so in these tables there are real simplifications, and in particular reorganization principle, which I think is very interesting. And
Where do you get the gamma functions from? Is that from the expansion of equation 2? Or
the gamma function, you mean what?
in the expressions in the table.
Okay. These things here. No, yeah, from there.
From there.
Yeah, you get them from the Gaussian normalization, higher order terms. Exactly. But at the same time, it's nice to compute them from the diagrams, in loop diagrams, because you see, especially this one of higher order, loop order, you see that it's a little bit more, it's a nice piece of math, and it's nice to recover this universal coefficient in very different approaches. So we could do it's also nice to compute all these numbers directly with a functional version. What's normally when I do a quantum field theory course, I do this approach, and I use hit kernel methods to evaluate the diagrams such a way always in closed form. There are a lot of nice pieces of math, and you can come out, you see how the counter terms combine, and you come out to this expression. I find this approach now more neat, because it's really focusing on the relevant information. Okay, so now that we have this, we can finally use the things to use the fact that the beta functions can be derived from the beta functions. So the easy model will always be so we know that now the universality class, and we have the beta functions. So remember here the 4 pi, they are nicely encoded here, you see. Okay, DC, L, there's a closed formula for them. This is DC alpha over L. So you just restore everything and you have this expression. So now we do two things. First of all, these are the dimension-full beta functions. So we have to go to the dimensionless beta function. This is the step that sometimes when we do quantum field theory, it's a little bit hidden. But away from 4, we have to go to the dimensionless, even if we use the same letter. When you do more hardcore AG, you are very careful in that, because you want to work in 3D, and there is a in any case, here we go to the dimensionless potential, which is a small letter. I take away a factor of pi. Here it's 4 minus epsilon, and there is the anomalous dimension, and the z goes in this way. So this transforms this set of equation in the equation for the corresponding dimensionless. So you see, you get all this part here, which is just the classical scaling, if you want, corrected by eta, by the fact that the right dimensionality of the field away from the Gaussian fixed point, what we call this thing here is d alpha minus 1 plus eta over 2. Okay.
What is mu in your expression?
Dimensionless variables.
It's about mu?
Mu is the mass scale, the mass scale, because away from the upper critical dimension, things become massive. I need to put that, but it will factor, then it factors away, okay? And now we can finally say, okay, now we can expand the potential in a Taylor series, okay? And then the anomalous dimension is fixed by the condition that we used before. So now it means that the beta v is the derivative with respect to the scale of this. So the beta v will have the same expansion, but with the beta functions here. So now these are my generating function. Now I can just plug them in, and again, just write a small mathematical code, and I generate all the beta functions. And so I have even a non-perturbation. Yes?
Just to, if you derived it considering the field to be at 0.
You take the derivative, so what you do is just this. So you see, so here you plug inside this thing here on here, and you expand, you truncate to a certain number of couplings, and you expand to every, and then you will have powers of the field here and powers of the field here, and you equate all of them. Okay. So what is here beta v will be expressed like this, no? Here then I will put also and so on. While This is the left-hand side. The right-hand side, you take the potential, you do the derivative, you multiply by this, you do the square, and this generates all the nonlinearities. And then you equate coefficients. You have two series, you equate them. Okay? And you can do this again. You just write a little code. And what is important is that this really generates all the relevant and marginal information of the theory. Okay, so first of all, I highlighted this because this is what we were looking for. This is the one loop and two loop contribution for the Ising model. The famous 17/3, if you did a quantum field theory course, you for sure have done this exercise. And it's a number that you remember because it's 17. In fact, it becomes 17 because it's a mix of anomalous dimension contribution and so on. But in fact, at the basis of everything, there is only A and B and C, which are 1/2, -1/2, and -1/6, which is much more clean. But you have the beta function of the mass, okay, or the gamma factor of the mass. You have all the possible contributions. And actually, here I've written also some irrelevant parts, but to say that this can be systematically done, and even by putting the irrelevant contribution, the mixing, you can do the same for the beta. So you really have all the beta functions. But again, all these numbers here that normally are computed independently, they just depend on these numbers that are in our table. So then this applies for every theory, every upper critical dimension, and it will also apply for any n and for any theory. So really, if you work in 4 minus epsilon, you only have to remember these 3 numbers. All the rest is group theory, if you want. Or the ability to construct invariants, which is what we're going to do. So now that we have the beta functions, we want to do finally for fixed points. In dimensional regularization, fixed point are trivial in one component case. It becomes a trivial, a very interesting algebraic problem in higher n. And this is actually something that you may be interested also in studying because it's a very well-defined problem. It's a problem that mixes group theory and algebraic geometry to find in a closed form all the solution of the system when we have more degrees of freedom. And we discuss this next week because it's really the main topic now. All these things shifts the problem of classifying universality classes to a problem in mathematics. In the end, in one component case, the problem is trivial. There's only one equation because all the couplings are 0 apart, and the fixed point is this one. Okay? So now, once we have the fixed point, what do we do? Well, we do what the RG is made for. We expand, so we have the fixed point, so we have our theory space, which is parameterized by all the couplings. So this is our theory space, our fixed point here, and then we go a little bit away, and so if this is lambda star, this is lambda star plus delta, okay? Which I write capital letter because I just changed the normalization for and then what I get is that the linear term is the new dimensionality. So this is the non-trivial dimensionality of this quantum field at this self-consistent criticality. So the Gaussian, the DC dimensionality will be this change, is dressed. These are the scaling dimensions. But then there is another interesting thing, the quadratic part, which normally was not so much. That now we have all of them because before you didn't have the full set of beta functions, and then you will say, okay, why should I compute this? But now that you have all of them, we write them in this way because we have that these numbers here are the OPE coefficients of the Gaussian theory at the critical. Okay? But then we have corrections. And these are non-trivial corrections to the OPE coefficients that were never seen before in the Epsilon-Expansion. But now that we have all the information, it's possible to have them. So we have our GOP coefficients. So now, let me just go to this slide before, at the same time, on the conformal field theory side, we know from conformal perturbation theory that a deformation of the conformal field theory has the leading part, which is D minus delta A, which is the scaling dimension in conformal field theory, and then that the quadratic part encodes the OPE coefficient of the theory. So now we have two characterization of the flow, which tells us how to interpret these pieces and all these other pieces. Okay. And so we have not only the spectrum, okay, which is very nice, but we have also an access to some OP coefficients, and in particular some, not all of them, but those which are dimensionless. Okay, those because the OP coefficients are dimensionful and dimensionless. And this was another novelty.
So can you go back to the slide where you did the wave function normalization? No, previous one. Yeah, here. So in principle, equation 2 is true for finite eta, right?
Yes.
And so what you're doing is when you computed these order epsilon corrections to the OB coefficients and stuff, then that's coming just from the first order term in equation 2.
Yes, it's coming from various. Yes, so it's.
I guess the question I'm trying to ask is that, you know, is it possible that you have control over higher order terms in the epsilon expansion as well?
Here or.
If I.
No, this approach cannot go beyond leading order.
Because.
It's difficult to extend it beyond leading order, this one. In the epsilon expansion, here I run, you see I wrote only the epsilon term because I know that the epsilon square term gets contribution from 3 loops, let's say in this case, which is not scheme independent, and so it's not certainty. And in fact, when we came here, there is a kind of paradox here because you know that the fundamental theorem of the RG is that if you change, now you make a change of couplings, okay, you change variables of coupling of this form, the spectrum is the same. This is the fundamental. But these coefficients in the beta function transforms in this way. So only they are invariant only when the dimensionality of the operator is 0, and this happens when you are at the upper critical dimension. So this proves that the blue things are CFT data. But now, in principle, when I just go away, this thing here is not anymore 0. But it happens that this thing here is at least of second order in epsilon. It must be like that. It's not easy to prove it, but it must be like that because at the same time, these numbers here are all functions only of A, B, and C. And actually, it's not difficult to write down everything just in terms of A, B, and C, and you will see. But A, B, and C, you have already proven that they are scheme independent. So there is this not being fish, not being meat of these terms that actually made us willing of computing these quantities purely in conformal field theory with the Schwinger-Dyson method. And every time we had an overlap, they came out the same. So it's true, the RG can also have correction to the OP coefficients. And actually they come out from A, B, and C again. So there is a lot of information that simply before, because things were done, let's say, not systematically, it was missed. And so this is nice because this is really the non-trivial information. And clearly now you can do this analysis, we can do it for any universality class of the one that we have. So that's the reason why we entered in, we also work in this CFT because we wanted to find a different characterization, realization of this 10/3 theory, and also we wanted to test if these OB coefficients were actually computed in the epsilon expansion were actually meaningful. And so there is an approach that has been done by various people, Nakayama, by Richkov, by other people, and we used that to see if our theory was there, and also to test this. And actually, the result here is just a summary. We can make a course only on these things, but the point is that, for example, in the Ising model, from the beta functional of the marginal and relevant sector, there are 3 numbers, 3 corrections that I can extract. And the problem is that even the Schwinger-Dyson plus CFT approach cannot compute all the OP coefficients, but it compute only some of them. Where they intersect is where I put them in Azul. And you see, in this case, we can actually have only one comparison for the Ising, but for the 3 critical, we have some comparison more, and for the theta critical, we have even more, and they all disagree. So actually, we are really constructing OP coefficients also in the epsilon expansion.
What does the E stand for?
See, is the Schwinger-Dyson equation plus conformal field theory is an approach. The one that generalizes the argument that we use for the anomalous dimension to the OP coefficient, basically.
And the components, for example, one.
Yeah, because these are the operators which are the power. Say in this case, those characters. So this is the field operator phi. This is the operator phi square. This is the operator phi to the field. Okay. So yeah. So the functional perspective has also this other game.
Can you compare the ones that are not in blue from bootstrap kind of stuff?
This is the bootstrap kind of stuff.
No, I mean like the numerical, the kind of numerical.
No, the numerical bootstrap, they never did it. This is the analytical bootstrap.
Sure.
There is also a group in India that was doing that. I don't remember, but we were citing many of them. They were doing these things for the ON models.
Right, and in the signals.
Yes, and also you can also compute various interesting things. The central charge, for example.
Yeah, they were able to do analytic bootstrap for like large spin. I think that was.
Then there is the large spin, which is another direction. Yes, there are various. Yeah, there are various, and so basically this was another revival of the Epsilon-Expansion because basically what you can do analytically even in the bootstrap is within the Epsilon-Expansion in a sense. So it's up near to the upper critical dimension. So it's the same kind. So this was a nice cross-fertilization of the various things. The numerical bootstrap is in 3D. And in 3D it's difficult. This expression cannot be continued to 3D at this order. Actually, there was one of the thing we wanted to compute at that time was really the OP coefficients with the RG, starting from ideas based like this one. Because if I have the full beta functions of and have them with an approach which is the non-perturbative one, which works in 3D, then I should just go there, expand around the fixed point, and I should be able to compare also this information. But then it's more complicated than one can think. But okay, so this was another interesting thing. And now, as I said, we can go on and we have our zoology of theory. So, for example, the Lee-Yang theory, we have our beta functionals. So this is interesting because this is the only non-trivial scalar universality class in 4 dimensions, but it's not unitary. What does it mean from our perspective? It means that the fixed point is imaginary. But it has a meaning in statistical mechanics. And again, having real controllable non-trivial fixed point in 4D is not so easy. So it's because there are the examples of supersymmetry, but if you want a non-supersymmetric theory which has a real non-perturbative fixed point, which you can put your hand in the fire, that is like percolation. This one I don't know many more. So it's, and we live in 4 dimensions. So if we hope the standard model has an UV completion which is non-trivial, be governed by a fixed point, and again here now you can, for example, obtain exact formulas for the gamma functions for the I. You can compute the OBE coefficients exactly, and again we can match them. Okay, and it's interesting because they are imaginary OBE coefficients, and they are computed when in a SUL. It means they are computed with the Schwinger Dyson and from the quadratic part of the beta function expanded around the fixed point. And this is our theory, let's say, which is very nice because it's really a theory that is the new one which exists in 3 dimensions. Is the one that has critical dimension is fractional, and it comes from a free loop computation. So it's really new. And also there is this intriguing fact that to reach 3 you have epsilon equal to 1/3, which is smaller than 1. So if if somebody can simulate this or can do it with the bootstrap not perturbatively, like we do it in the bootstrap not with the Epsilon-Expansion, but the problem is that it's not unitary. So most of the techniques they have, they don't really apply, and there are also people doing it for percolation, but I never managed to speak with them or propose this. It would be very interesting because this is really a case where you can say, okay, maybe I really push perturbation theory. If I have epsilon, maybe this is one case where the Epsilon-Expansion can converge. And so this is still a local problem in a sense. It would be a nice thing to have one example where the Epsilon-Expansion converges. And so this theory is interesting. Again, the fixed point is complex. So it's like the critical version of the Lee-Yang. So it's not as physical if you want, but it's very interesting. Again, you can do a lot of things. Here it happens that the Schwinger-Dyson equation and CFT are less powerful because, for example, they are not able to give you the critical coupling in terms of epsilon. So the RG is more stronger in this case. And so we can only compare ratio between universal quantities, but all the ratios, they agree within the two approaches. If you read the Adam, Hijackers Guide to the Galaxy, this is a nice ratio. So this was nice to have a universality class. And also, again, if you like a little bit of math, to see these terms coming out from loop diagrams or from, that's the reason why the CFT is actually not able to do this, because if you have this relation, you actually have the beta function. But the beta function involves this structure. So I do not see how from this analytical bootstrap manipulation, you can generate such a complicated structure while I can see it coming from a three-loop integral. So there must be some new ideas in the CFT side if you want to recover that. And then there is actually a formula for the net. We have seen the multicritical. AEN and CN, basically, we computed them with this argument of scaling. If you generalize the argument for the anomalous dimension, you actually, with the same effort, you get this formula. And with similar effort, so this was the leading order, which are, but then there was a very nice another strategy done by Osborne, which is the father of many analytical results, even in the bootstrap, that they did a calculation, which is a perturbative calculation, but not based on the loop expansion. And they were able to, for this class of models, to get the full formula. And it's nice because you can check, so they were able to compute the coefficients, while this formula, we have it from our argument. It's nice to check because it's non-trivial that our little algorithm actually generates all the monomials that come out from this. And okay, here, so for example, you can have the gamma 1, gamma 2, and gamma I for all multi-critical models. You can extend many, you can have many results. And actually what we showed is that this formula can also be analytically continued to fractional n, and it will give the leading order of the odd models. So from this formula, analytical continuation recovers this formula, for example. So there was another interesting. Okay, so, and then there is the final case, which is the simplest one, which is the Sine-Gordon case. So if you remember our table in D equal 2, the theory that we have in D equal 2 is is a theory that has only a contribution at one loop, no higher order contribution. So in this case, the beta function is exact. And now we can do something different. We can solve the fixed point at the functional level without going to the beta function, because this is something I didn't mention. This is just one approach to finding solution. It's the place where you find for solutions which are exist in a Taylor series. But in general, the RG is something in a functional space, infinite dimensional, and you should look at functional equations, not only. And so all the beta functional can be used in that direction, and it's another line of research. But in this case, let's just look for the zero here, and this is just the cosine. And this is the Kalman phase. So this is really reproduces the renormalization of the Sine-Gordon model. Something that we should look at, I have the analogous of this, but for example, the ON model or the Potts model. And I've never seen that. And it would be nice to study what the fixed point mean for the multi-component cases. And there is a variety, because they become partial differential equations, which could be solved. This is another project that we can do when we see. I will show you an example of that. Okay, so this is somehow, with this we have achieved the understanding of one component universality classes represented by Lagrangians of the form that we have. We know where to expect them, in which integer dimension, we know what is the form of their functional, we know how to compute, which are the quantitative information. We know that from these simple formulas we can generate all that we knew before and also something new that matches with conformal field theory. So we have achieved a higher level of understanding, I will say, in this thing. So now we can start, as usual, we know something, since we have every method we use is basically approximate. In any case, to know something means to know it from different perspectives. So here we have seen that to make universality classes in perturbation theory is a little bit strange that for each universality class we have to choose a different upper critical dimension. And somehow in our formalism, even in, for example, in 3 dimension we have, I don't know, for example, we have the Li-Yang, let's say, and the 10/3, and this they live in 3 dimension. So these two theories coexist. So there should be a flux between them, but in the way in which you construct them with this, this is the drawback of dimensional regularization. We do not see this interconnection because to construct the RG of this, we have to work in this dimension. To construct the RG of this, we have to work in this dimension. So it will allow us to see the flow between fixed point only when you have a multi-component. But in principle, in 3 dimensions, this exists, and one will be the deformation of the other one or something like that. So there is another approach, which, so again, as I said, now we have constructed the theories around the upper critical dimension. Now we want to go to, and here we know them as minimal models, okay? But in the middle is a land where we only have approximate approaches. And the two main, there are 3 approaches. The original one is numerical simulation, Monte Carlo. We have the non-perturbative RG, so a version of the RG which is not based on perturbation theory around the upper critical dimension. And then there is the bootstrap. Okay, these are the kind of tools that we have. But in particular, simulation and bootstrap, which are numerical, they have such an investment that, okay, you should know what to look at and which theory to expect, otherwise. So it's useless that I try to construct an icosahedral theory in 3 dimensions, because the RG, we will see, tells us that there will be no fixed point with icosahedral symmetry in 3 dimensions, but in 2D, there will be one. So you can do this effort. The non-perturbative RG will deserve a course. Actually, some years ago, I did a course here on that when I was coming more frequently. And I don't know if you know this approach. It's called the exact normalization group approach. And it's based on an exact equation, which is an exact normalization group equation, which is called Wetterich-Morris equation. It's the Legendre transform of the Polchinski equation. And it's a closed equation for the effective action, but the effective action that depends on the scale. Because as soon as we are away from a fixed point, there is a scale. So you have a scale-dependent effective action, and you have an equation that tells you how to flow from one point to the other point in theory space. Okay? This is me. So here you have gamma mu, here you have gamma lambda, and here you have the full effective action. So this object interpolates in the UV and in the infrared. Clearly, if this UV goes to a fixed point, I can set lambda to infinity and I achieve non-perturbative normalization. Otherwise, in the infrared, I can hit a critical theory, so I can also construct critical theories. So it's a very versatile, if you want, it's really an independent realization. Actually, it's a mathematically grounded definition of the quantum field theory, because the fundamental idea of the RG is that an RG step is the difference of 2 path integrals. And so it's a one-dimensional integral. This is well defined. The theory of functional integration is the theory of trajectory in theory space. And depending on if you have or not a fixed point, you can take the limit, the continuous limit, and all these kind of things. So this thing here, provided you can define a nice space where this gamma lives, is a well-defined framework, which is the whole subject of investigation, okay, which I've also worked on for several things. Actually, my main papers are applying this to quantum gravity, which is and proving that within this kind of approximation there is asymptotic safety. But this is it's completely, but it's actually the source of my interest in being able to construct universality classes. Because, for example, in quantum gravity, we see the fixed point from this perspective, and it would be nice to have other perspective. What we achieve here with the equilibrium statistical mechanics universality classes is that we really see them from conformal field theory, we see them from the non-perturbative approach, and we see them from perturbation theory. And in particular, here I'm interested in my universality class, which I characterize in 3 different ways. So I believe that this universality class is there. So this approach, you can do something similar. You can get beta functionals and they have some equations. But these equations, they are all truncations. So again, the full system will have the running of the potential, of the wave function, normalization, and all the other functions, and they will be entangled.
So the R there is the computer solution, right?
Yeah, this thing here I didn't mention is the regulator.
Right.
It's an infrared regulator that has to decay sufficiently.
And the subindex
U is the scale.
scale.
Yeah, and sometimes you use kappa for this, but it's just
Yes.
the normalization scale.
Okay.
Since in perturbation theory normally use mu, I keep the consistently. Actually, the idea of working functionally comes from the functionality, because in functionality you always work functionally, and you know that this can be useful, and in fact it was. So what I want to show here is that the simplest embodiment to answer the question, which are the universality classes? So we want now to answer with this approach exactly what we answered to have our table. So in the non-perturbative approach, I have this equation, you see, which is similar to the equation for the potential, but this is the non-perturbative version. And in fact, you see that it has a different, so the scaling part, the canonical scaling is the same, is the non-perturbative part, which if I expand, I will recover some term of the other side. Now, what is interesting is that this equation now encodes all the universality classes in all the upper critical dimensions, all the odd, the even models. And in particular, but I have to stay functional. So I have to solve this. This is an ordinary differential equation for the fixed point. So the fixed point problem is not anymore an algebraic problem. It is a problem of ordinary differential equation. This is a nonlinear differential equation. And in particular, it has, if the symmetry is zeta 2, you have these two conditions. So we wanted even. And then you have only sigma, which is, let's say, the value of the cavity, the mass. So what is interesting is that you can make a plot where so the solution, you demand them to be valid for every value of the real field. So this, you discover that the quantization condition for fixed points comes from the regularity of your potential. Your potential has to be well defined. It cannot have singularities. And then you basically shrink all theory space in one line, because you basically discover, you can prove that in the family of running potential, all the fixed points lie on a one-dimensional submanifold that you can parameterize with sigma. And then sigma equal to 0 is the Gaussian fixed point. Sigma, a little bit negative, is the Ising fixed point. And then you will see, in particular, and this has no problem, you can work with arbitrary b. So when you come down from above 4, in 5 dimensions you have only one fixed point. In 4, you see the Ising branching out exactly like the Epsilon expansion. And then when you reach 3, you see the other one branching out. And in particular, here it's not clear, but you see them as spikes. So in this plot, you basically integrate numerically this equation with the different initial condition sigma. So you're basically going along this one-dimensional submanifold, and when there is a spike, your solution doesn't have singularities, because this is basically the position where you find the singularity. So all apart a finite set of initial conditions have a singular potential. And so with this plot you can make it dynamical, and when you can make video, for example, that when you can come down in 5 you have only this, the Gaussian, and then below you have the Ising, and then at 3 you have the tricritical, and you at the same time draw the effective potential, and you see that they are, and in this way you really see all fixed points branching out exactly at the upper critical dimension that we have seen, or the upper critical dimension where perturbative diagrams can have fixed point.
Sorry.
And then, yes?
So what is the definition of unitary models?
Yeah, this is what we said. For us, they are the even models. Okay? Because they are odd models, they have complex coupling, I will show you, so you have to split the potential in a real and imaginary part. But what is nice is that you do this, and then for each point you can do the stability matrix, compute the critical exponents, and draw how the critical exponent, the spectrum evolves with the dimension. And this goes to an infinity of fixed points, which are the minimal models. So in this way we can really trace, we can really draw these lines. Yesterday I didn't have time to answer, but one realization of this kind of cartoon is this kind of plots, where you can really draw the spectrum branching out and see how it evolves continuously with the dimension. And here the dimension is this parameter, clearly, the dimension, which if you want is the spectral dimension of the structure that you're working on. Then if these theories in fractional dimension have a meaning, I try to realize them in fractals. It's not easy to realize a critical phenomena but probably they are there, and if they are realizable on a fractal, for example, I think that the critical exponent will be this one. But in any case, what we're interested is the integer dimension, but more generally, we're interested in the evolution of theory space. So we really see, so basically, we really recover that we see the Ising, the tricritical, the tetracritical, and so on. So this is a different perspective on this complex thing, which is the problem of universality classes, and we have perfect agreement. So it's, and then we can also do it with conformal field theory, for example, conformal field theory, as we did for the OP coefficients. Then one can go and study things more in a more sophisticated manner, and one can really find. So now this is to resolve the multi-critical models in 2D. I will have now, if I have both beta V and beta Z, I have a complicated system of parser of ordinary differential equation. But the solution of this should be the minimum models. But now I'm not imposing conformal symmetry. And they come out as now in a bidimensional plot. And they come out and they give a reasonable value. You see this is beta, and they come out like in a spectrum. And if you look at them, you know, Ising model is 0.25, the other one is 0.15. It's a crude approximation quantitatively. But qualitatively, you really resolve all the minimal models, again, without using the symmetry. So it's really the RG who is really able to show you all these fixed points. So it's basically another way to resolve this thing here. And what is interesting is that we can also do it for the odd models. So basically what we do is to work with the complex potential, with this parity symmetry. Now this is the symmetry that replaces zeta 2. And we can do something similar. And this is, for me, is one of the most, this is a very precious picture for me, because you see this is the Young model in 4 dimensions. So there is a fixed point in 4 dimensions. So again, it's not easy to have something in 4 dimensions where we are sure that there is a fixed point. And also we have this what's called Blaum-Capel, this tricritical model. So the 10/3 exists in 3 dimensions. So you see it also on the non-perturbative side within this approximation. So now the 10/3 we have constructed with the perturbation theory, with CFT, and with the non-perturbative RG. So we have 3 independent, will be nice to have a simulation and then will be nice to have more precise determination of the critical properties to see, for example, is the Epsilon-Expansion as well. But yeah, so this is to prove that our argument that we did yesterday is actually working. And it's actually true that in perturbation theory there are these contributions, a higher loop, and in fractional dimension. So there is a lot of information that was not looked at. Okay. So let me see. Okay, we're gonna stop here for today. If you have some questions or something, we can discuss it. Or okay, yeah. Hope it's interesting to you. And
just watching the graph, how did you know that you have a fixed point? Which is because of the shape?
Yeah, okay. So basically, these equations are not so easy to integrate.
Okay.
So you can see by analyzing the structure of the singularities that emerge for the majority of initial condition that the majority of the initial condition have singular fields. And so you ask yourself, when are they not singular? And then you can draw this kind of diagrams to see the place where this happens. Because when there is this kind of thing, something is happening in the singular structure. And so this is a technique that we have invented to look for the fixed points. You know, because now you're looking for a fixed point in an infinite dimensional space. So it's not just like an algebraic problem of looking for the zero of the beta function. It's something more complicated. Okay, and this is one technique. There are many. They all agree on this. So you really see. So by working hard enough, you can resolve these theories of the critical property with precision. And this is actually what with Nick in the group in Montevideo is using one approach to characterize universality classes. And actually, one of the things that I want to do, since the next week we're going to see that in 4 dimensions, so now we're going to move to the multi-component case. And in particular, when n equals 4, the critical 4, we have discovered 3 new universality classes. So we will see that n equals 2. Okay, we will focus for the moment on the critical 4 and the critical 6. But let's say that what is really interesting to us is the critical 4. So we have in n equals 1, we have the Ising. N equals 2, there is basically there is the O2. There is nothing really interesting happening. So this is the critical 4. Here there is Ising times Ising, and the new one is O2. N equals 3. There is always products of the lower ones where we are, but there is basically O3. There is the cubic, and then there is zeta 2 times O2. It's called B fundamental. So there are 3 of them. In let's say the heroic times of the Epsilon-Expansion in the 80s, they, under one condition, they proved that, because then this theory has the particularity that has 2 invariants of order square, 2 mass terms. So at that time, people were imposing the trace condition, and they proved that there is only these 2. With this formalism, let's say we have enlarged and dropped this condition, and we have found that there is only this one more. N equals 4. The things explodes. It's actually something I'm working on. Since the number of couplings, because when we do the general theory here, the number of couplings is 5, here is 15, and here is 35. Then we will see that what we basically do is not all these couplings are independent, because there is an overall ON symmetry of the cinetic term. So you using some group theory, you actually reduce them and simplify. By doing this, we were able to find all the solutions, and we added this one to this one. Even though this one was previously known, what we proved is that in n equals 3, there are only these 3. N equals 4, for the moment, we don't have a way to prove, to show the classification, because it's very complicated. So what we have is partial numerical results, which means you take this system of beta function, you put some of them to 0, or there is a nice bound by Stergio and Richko, which says that maybe around the border of this bound is more probable to find solutions. And you try them, and by doing this, we found some new fixed points. So new theories we will see them. Now, what is interesting is to see if this theory is constructed perturbatively, can exist non-perturbatively, and calculate their critical exponent, even though, for example, an energy approach like this is less efficient than the bootstrap, but it's something that a master student can do. So we can do that, and we can have the first guess for the critical exponents. Okay, so there are many things. For me, theoretically, it's very interesting to find a way to classify all of them. And here is where you have to go. It's an intersection between algebraic geometry and group theory, I would say. Which again, we can also work a little bit on that next week if for you these things are interesting. So now, this is one of the goals, because now this means extending our atlas to every n. So now we have, for every n, we have a table. What is really nice is that we don't need to do any new computation, because we will see tomorrow that actually it's trivial fact that the beta function for and n equal 4 are the same one. So this is really if I have to convince you why to do this, what we did about the functional approaches is not convincing you yet. This one will be the thing that should convince you, because we have v second squared, and here we have 1/2, no? This is the conclusion. This can only become 1/2 ij vji, and nothing more. But now this one can be applied to any model in any component. So the beta function of the ON model, the beta function of the standard model, whatever, they are inside here. Okay? So this is very powerful, because now we basically add indices to our table, and we have the general set of beta functions. And now that we have the general set of beta functions, we have two roads. Either we say, okay, now I specify a symmetry, and I explore all the theories with those symmetry, and this is what we're going to do with this Platonic field theory. So we're going to take the symmetries of this class of symmetry, which generalize this, and the tetrahedral symmetry, which is the one of the Potts model, to the. But now, since we have all the beta functions, already we can, and in particular now we know that some symmetry, there is a relation between the upper critical dimension and the symmetry, because to be able to have a theory with a certain upper critical dimension and a certain symmetry, this symmetry must have an invariant in that representation of a certain power of the field. Actually, the smallest invariant, which is peculiar to that symmetry, is the one that dictates which is the upper critical dimension and then where I can find. So we need to learn how to make invariants, and we're going to do a nice piece of math which is called the Mollien series, which is something that for every group and representation, it gives us a map of which kind of invariants. And by crossing that information with this one, we already know, okay, this symmetry can be realized here, and then we immediately construct the beta function and compute the stuff. So one line is that I fix the symmetry and do whatever I want. So the first thing we're going to do is the ON model. But we are not only going to do the ON model, we're going to do the 3 critical ON model, the 4 critical ON model, and the 5 critical, which amounts, if you have to do it with all the links, as something like an 8-loop calculation that we do without having to do any new calculation, because in any case we use these coefficients and so on. So there are these two roads. So we're going to explore a little bit fixed symmetry, and then the general problem. I fix n and I consider all. So now the RG is the one who predicts the symmetry. So we are computing the symmetry. So at the end of this road, we really know which are the symmetries realized in nature as fixed points. So in principle, one can imagine going more, the symmetries of the standard model are emerge from computation where we do the RG of the standard model, so we have also all the other stuff, but with the most general symmetry, and we see that, okay, SU2 can appear and the other one cannot appear. Because there are a lot of groups, for example, that have 3-dimensional representation, but the RG selects only this. So now you have this connection. So this is another end, and this is really turning upside down, no? Now the RG comes before the symmetry in the last part. First we do the RG with the symmetry and we see the empowerment that we have. So this is the second part. Okay. Oops.